Hello everyone, and welcome to the video on differential equations involving growth and decay functions. A lot of these things are going to be pretty familiar to you because we've dealt with growth and decay functions last year in pre-calculus and in Algebra 2. Some of the things you're going to remember on this one you'll recognize as we go through this is going to be the old PERT formula for continuous compounded continuous interest problems. So our objectives for this video are: 1, use separation of variables to solve a simple differential equation, and then use exponential functions to model growth and decay in applied problems. First, let's talk about separation of variables. Now, I tend to use Leibniz notation, and that's where we use dy dx instead of y prime. To me, it makes it easier to separate the variables and to actually see the separation and work with it from there. And so what you want to do when you're using separation of variables, it's exactly what it sounds like. You want to get everything with a y on one side and everything with an x on the other side of the equal sign. And then what you're going to do is integrate both sides to get a general solution. Now, the one thing you have to keep in mind is that when you get everything with an x or a y onto one side is going to be dy, the other side is going to have a dx. Please also remember the dy and the dx cannot be in the denominator. That's the only real condition you have with this. And then you're going to apply any initial conditions to find a particular solution. So once you have the general solution, our goal will be then to find a particular solution for that differential equation if we're supposed to do that. Let's take a look at an example here and how this works. In this case, in this problem, what I have is that y prime is equal to 6 minus y. Well, the first thing I'm going to do is replace the y prime with dy dx. So I have dy dx equals 6 minus y. And now I want to separate the variables. So I want everything with an x on one side, everything with a y on the other. Now the one thing you have to be aware of here, a lot of people will try to go on something like this and add y to the other side and then multiply by dx. The problem comes in there then really when you multiply by the dx, you're not going to get just the x's on one side because you have to multiply that added y by dx as well. So really what you're really going to be looking for to separate the variables for the most part is going to be multiplication and division. In this case, what I can do is I can divide both sides by 6 minus y and multiply both sides by dx. And when I do that, I'll get dy over 6 minus y equals dx. At this point, I can now integrate both sides. Now notice I'm going to be integrating the left-hand side with respect to y because I have the dy, and I'll integrate the right-hand side with respect to x. Now, when we look at this one, you should recognize that one as a natural log. If you don't, you can make the substitution. Let u equal 6 minus y, and then du then is going to be negative dy. And you can make your substitution there, but the end result is that this thing on the left is going to be integrate to be negative natural log of the absolute value of 6 minus y, and the integral of dx is going to be x plus c1. Now you'll notice I just put the constant on one side, and that's something that we will always work with. We'll just put a constant on one side. We don't have to have a plus c on both sides. So we're just going to add the constant. And now what I did here is I went and multiplied by the negative 1 to make that a positive natural log of the absolute value of 6 minus y equals negative x e to the, it's going to be the opposite of x minus c1. And then I want to solve it for y. So the first thing I have to do is undo the natural log. And to do that, I just take e to both sides. So I'll get 6 minus y equals e to the minus x minus c1. Now, why don't I have the absolute value signs there? Well, I don't need the absolute value signs because I know that e raised to a power is always positive. So therefore, I know that 6 minus y, the absolute value of 6 minus y and 6 minus y must be equal to the same thing. And so by laws of exponents, I can break this up to be e to the opposite of x times e to the opposite of c1 or negative c1. Now this part right there, that is just a constant. That's a e raised to a constant is itself going to be a constant. So that's why we replace that with c. And so I have 6 minus y equals c e to the opposite of x. And then solving it for y, I can subtract 6, then multiply by -1. I get my general solution, which is y equals 6 minus c e to the opposite of x. Take a minute, pause the video, make sure you're comfortable with everything I did in this problem, in this example, and then once you are, then we can move forward. If you have questions, make sure to note them in your notes, and so that you can ask them in our next class. Here's an example of an application problem. We have the rate of change of p is proportional to p. When p equals 5,000, p is equal to 5,000, when t is equal to 0, and when t equals 1, p is 4,750. And they want us to find p when t equals 5. All right, now first of all, what you need to recognize here, they tell us that the rate of change of p is proportional to p. What that does give us a differential equation, and it tells us, if you remember back in Algebra 2 when you did variations, when you said something like this, there was it would tell you that the rate of change of p, dp dt, is equal to k times p, where k is a constant of proportionality. What that constant is, we can find that information based on the problems that we have. But for right now, when we set this up, I'm just going to say dp dt equals k times p. This type of situation, whenever you see that a rate of change is proportional to something, yet it's always going to be dp dt or d whatever it is equals k times whatever it's proportional to. And so by separating the variables here, I'm going to multiply both sides by dt, and I'm going to divide by p. And so I get dp over p equals k dt, and I integrate both sides there. And when I do that, I get the natural log of the absolute value of p equals kt plus c1. And then solving that, again, I undo the natural log by taking everything raised as the exponent on e. So I get p equals e to the kt plus c1, which again, very similar to what we did last time in the last example. I know e to the kt, that's going to be e to the kt times e to the c1, or p equals c e to the kt power. So this right now is our general solution. Okay, what we're asked to find is, we want to find what happens when find p when t is 5. In order to do that, I'm going to need to identify values for c and k. Well, the other thing you should recognize from this is that this formula right there should be very familiar to you. It is the old PERT formula, if you think of it. In terms of the problem. So this, and when we talked about this last year, and I'm sure when you talked about it in Algebra 2, that I told you it was very important to remember not letters, not what the letter stands for, but place value. So what I know is happening here, C, in that place value, if you remember, that is always the initial amount. And the initial amount is when t equals 0. So from this, I know that when t equals 0, p is 5,000. So I know my initial amount is 5,000. So that tells me that in this case, c is 5,000, and so p is going to be 5,000 e to the kt power. Now what we need to do is find k. And so I'm going to draw that line there. And to find k, I need to use this other piece of information I know, that when t is 1, p is 4,750. And so what I can do at this point is I can put 1 in for t and 4,750 in for p. And I will get then 4,750 equals 5,000 e to the 1, or k times 1 power. That is a k right there. Okay. And now what I'd like you to do right now is pause the video, and I want you to solve it for k. Welcome back. You should have got that k would be equal to negative 0.05129, about equal to that. Let's see how it came out. So at this point, we plugged all that information in. The first thing I have to do is divide by 5,000 because I want to solve for k. So I divide by 5,000, so I have 4750 over 5,000 equals e to the k. And then take the natural log of both sides. So I have the natural log of 4750 over 5,000 equals the natural log of e to the k, which you should remember that when you take the natural log of e to something, that those are inverse functions, so they undo each other, and the result will just be k. So plugging this into my calculator, I get k would be about equal to negative 0.05129. And so our particular solution to this differential equation problem is P is 5,000 e to the negative 0.05129t. And now what happens after that, because we want to find out what happens when t equals 5, I really just take that problem, put 5 in for t, and when I do that, I'm going to get an answer. Since this is like a population, I can really take it to just round it to the nearest whole number. I find that when t is 5, when t equals 5, P comes out to be about 3,869. And that would be my answer, the final answer for this problem. As before, take a couple minutes, look over this problem, make sure you are comfortable with everything I've done there. If you are not, please put a mark in your notes and be sure to ask about it at our next class. Another situation that we can have with this is what's called Newton's law of cooling. And in Newton's law of cooling, what that says is that the rate of change of an object's temperature is proportional to the difference between the object's temperature and the temperature of that surrounding medium. So, in this case, we're going to have a container of hot liquid, which is, we're going to say that is 160 degrees Fahrenheit, and it's placed in a freezer kept at 20 degrees Fahrenheit. After 5 minutes, the liquid is cooled to 60 degrees Fahrenheit. And we want to know how long will it take to cool to 30 degrees Fahrenheit. Well, first thing we have to do is set up a differential equation. Now we know by Newton's law of cooling the rate of change of an object temperature, so we're going to let y equal the object's temperature. Otherwise, we could, if we use t's, we get to be too many t's. So I'll let y equal the object's temperature. So I know the rate of change of the object's temperature is directly proportional to the difference between the object's temperature and the temperature of the surrounding medium. So in this case, dy dt, the object's temperature over the change in time, dy dt, is directly proportional to the difference between the object's temperature y and the temperature of the surrounding medium, which is the 20 degrees that the freezer is kept at. So it's dy dt is going to equal k times y minus 20. And doing the separation of variables, I'll divide by y minus 20, multiply by dt. I get dy over y minus 20 equals k dt. I integrate both sides, left side with respect to y side with respect to t, and I get that the natural log of the absolute value of y minus 20 equals kt plus c1. Now in this case, we actually don't need to use the absolute value symbols there because I know that in this case my object, the temperature of my object is already starting out very hot, above 20, and so we're bringing the temperature down. So I know that y minus 20 is going to be a positive value. And I'd go through, and when I solve that, I get that y minus 20 equals c e to the kt. Now you can add the 20 to the other side. You don't have to. Obviously, in some problems, when you look at the answer, they'll ask you to solve for y. But in this particular one, from what we're going to be working with, I would actually just probably leave it as y minus 20 equals c e to the kt. Now what we're going to take a look at, though, is we're going to use the information that I know. I know that when t equals 0, the temperature is 160 degrees. The other thing I know is after 5 minutes, when t equals 5, the temperature is now 60 degrees. So for that, here's that information right up here. And I need to use that information to find some things out. Now, one mistake students make with a problem like this is they think of this as a PERT problem because it looks like a PERT problem, but it's not. Okay? We know that when t equals 0, y is 160. So if I plug that information in, I get 160 minus 20, which will be 140, equals c e to the k times 0, or C e to the 0 power. E to the 0 is 1, so in this case I find that C is actually equal to 140. So coming from here over to here, I know C is 140. So I now have y minus 20 equals 140 e to the kt. And now I use my second piece of information, that when t equals 5, y is 60. So I put 60 in for y and 5 in for t. And I get that 40 equals 140 e to the 5k. Dividing by 140, 40 divided by 140 will be 2/7 equals e to the 5k. Solving for k, I have to take the natural log of both sides, then divide by 5. Now when you put this into your calculator, make sure you close off the natural log function or else you're not going to get the correct answer. So you take the natural log of 2/7, make sure you you close off that natural log function after the 7, divide that by 5, and you're going to find that k is about equal to negative 0.25055. And so, in this case, our particular solution would be y minus 20 equals 140 e to the negative 0.25055t. Now notice I keep more decimal places. The other thing to remember on this, you want to keep as many decimal places initially as possible. Limit the amount of round off error that you have, because if you were to round it to 3 decimal places here early on, that's going to create more problems at the end, and your answer won't match up with what would be on the test for the AP exam. Keep this as much as possible. So when I solve that, I'll get 10 equals 140 e to the negative 0.25055t, and I need to solve it for t. So I divide by 140, take the natural log of both sides, and then divide that natural log of 10 divided by 140 by the negative 0.25055, and I get that t is going to be about 10.5 minutes. Make sure to do these calculations. Make sure that you get those to match up. If you don't, double check your the problem is more than likely going to occur with closing off the natural log. If you don't get those, if you can't figure out what the issue is, make sure to note it and be sure to ask me in the next class. This does now conclude the video on the separation of variables and working with growth and decay differential equations. So in the next class, we might do a couple examples, a couple more examples, at least in terms of the separation. But besides that, we should be in pretty good shape. And with that, I will see you in our next class.